没事吧？这样的，手托着下面，这样可以保持相机稳定。
Good morning, everyone. We are just about to start our second morning session with 3 talks, 2 award lectures, and I will be chairing this session. My name is Yuri Gogotsa. I'm from Drexel University, and I will actually be giving the 3rd talk today. But the first lecture is an award lecture of Professor Julia Greer, who recently was endowed as a chair professor, Ruben F. and Donna Medler Professor of Material Science, Medical Engineering and Mechanics at the California Institute of Technology, and you have heard about her achievement and awards earlier today. So without further introduction, Julia, the floor is yours.
Thank you so much. Can everyone hear me? I've never been accused of being too quiet, and I don't want to wear a mic. So can everyone in the back can hear me? So I'm saying that right. All right. So you've been staring at this title for long enough, so I'd like to begin by thanking the organizers, but it is a huge honor to receive this award, to be here, and thank you all for being here as well, for inviting me. All right, so you've been staring at this title for a while, so materials by design probably makes sense, and then you look at the second part of the sentence, and you see 3-dimensional nano-architected metamaterials, and you're wondering, okay, I think maybe I understand each one of these words on its own, but why they belong in the same sentence might be a little less clear. So the goal for today's talk is to convey to you why that is, in fact, appropriate to put them all in the same sentence. So, but I'm here because of receiving this award that AAAFM-Heeger endowed, I guess. So what I'm showing you a picture of Alan, and then of course he's widely known for his pioneering research on various types of polymers. So I will tell you a lot of stories about polymers today. But the lesser known fact about him is that he's actually a huge theater now. And so if you love theater, you can see that there are all these plays that he's been in. And so I'd like to begin, I guess, and to motivate my talk by showing you this, inspired by this theater situation. So I also happen to have a theatrical play. Can you hear anything or not? That's the whole point of these 2 mic people. Maybe it's just starting to. Well, I know.
The volume is up, yeah, it's just down one time.
Why nothing? No, not muted anymore, right? I wanted to show you this, which is my theatrical thing, but it's not willing to. Oh, the wheel of death. All right. Well, I wanted to show this to you, so maybe when we talk afterward, I don't know why he's not willing to cooperate. So I also have a theatrical inspiration, I guess, and I was hoping to. Musique, and this is Rachel Warby, she's the director of Musique. And so I did a performance called Nano-Rap. So I was performing a piece of music while talking about my research simultaneously. So I thought that would be very appropriate to show. But since this thing is not willing to cooperate, unless Jens, I'll just go back to science. All right, someday, maybe afterward. All right, computer. Okay. Now, we are all familiar with a situation like this. You go to the store and you need to get all these things, right? So you really, really need all these things. And of course, you have plastic bags, which you can't get in California anymore. Don't hold out, right? So this is not the only example of materials that are just not quite well suited for what we need. So from the wine glass that never makes it to the table to the balloons, so they are really meant to have Christ children. So these are all examples of materials that are lightweight, right? So they're lightweight, but because they're lightweight, they're weak and easy to damage and tear. Now, in contrast to the materials we know to be strong, which is certainly not lightweight, but very strong, right? So some of us are very intimately familiar with these, as we all just flew in. So the Boeing 747 weighs almost 1 million pounds, and so if you do a back of the envelope calculation, so I just flew here from Atlanta last night, so my ticket here should have been $33,000, right? So certainly very expensive. So the Dreamliner already is reducing the weight by quite a bit, and so there's a lot of fuel savings here. So materials that we know to be strong come at the price of being heavy and expensive. Now, other examples, of course, materials that need to be very lightweight are, solar panels here in California, very relevant. Do you remember that space elevator that we've been discussing for the last decade or so? As far as I know, we still don't have one. So the reason why we don't have one is because of this very busy plot. And I'm choosing to show you a strength, but it can be any mechanical resilience attribute. It could be toughness, it could be stiffness, it could be fracture resistance. Anyway, it's a function of density. And look at all these colorful domains. And so what these represent are all the materials that we know how to make today. And what comes out right away is that we are very good at making materials that are simultaneously strong and heavy, or lightweight and weak. And what we're not so good at is hitting the so-called white space. And that is making materials that are relatively lightweight, at least the relative density is low, and mechanically resilient. So how do we hit this white space if everything that we know how to make today is already here? Now, I'd like to point out that this is a long lock plot, so even a modest increment within this space already represents a substantial change. So it's sufficient to get even over here to have an effect. Well, the way we do it is we draw our inspiration from what exists today. So when you look at the Great Pyramid of Giza, this is the largest stone man-made monument. You see that it stands about 150 meters tall, and it weighs nearly 6 million tons. So that's very, very heavy, right? So now, in contrast to the Eiffel Tower, and maybe some of you have been to some of these things, which stands twice as tall, and it weighs 1,000 times less. So that's 3 orders of magnitude less. And it's just as mechanically resilient. They're both still standing. And I suspect that there were a lot fewer slaves used in the construction of the Eiffel Tower. So what that tells us is that we can make structures that are mechanically resilient without using quite so much material, right? So we began this research by collaborating with HRL, which is actually not too far away from here. And so what we made is a nickel microlattice. What you're looking at is the world's most normal dandelion. There's nothing photoshopped about this picture. This microlattice is made out entirely of nickel. And you can see it's hardly perturbing the dandelion at all. It's exceptionally lightweight. In fact, if I were to hold one in one hand, one of these in one hand, and a feather in the other, and to release them at the same time, the feather would fall down faster. It's just exceptionally lightweight. But what we want is not just the lightweight. We want a combination of the lightweight and strength. And for that, we have to go down 3 orders of magnitude in dimensions. And so what you're looking at are examples of nanolattices. These are all made by various graduate students in my group. And what you can see, first of all, is that we're not limited in periodicity, and so this is a micro TARDIS, those of you who are fans of Dr. Who. So this is about 1,000th of your hair diameter, these are very small. Now, when you look at the lattices, the obvious part that comes out is that they're cellular solids. So they're very porous, right? So very, very lightweight. But the less obvious part that may not emerge right away is that the tubes that comprise these woven architectures are hollow. And so we're effectively constructing 3-dimensional interwoven networks of straws, very, very thin-walled cylinders, and the wall thickness here could be on the order of 5 to 10 nanometers. So this single material embodies every length scale from some nanometers, just maybe 5 or 10, to hundreds of nanometers, to microns, which is the dimensions of the unit cell, to hundreds of microns, the dimensions of millimeters and centimeters. And this is why it's appropriate to call them metamaterials, because at these very small length scales, nothing is independent of one another. They're not structures, and they're not materials, they're actually both. And so to illustrate this, I'd like to first of all, prove to you that they are in fact very different, or materials behave very differently at a nanoscale. When you look at some typical metals, so this is gold, silver, copper, so your earrings, those of us who wear earrings, we know gold and copper to be very malleable, right? So now, if you look in these metals in their single crystal form, and you plot their strength as a function of size, you see this tremendous strengthening, again, a log plot. And what that tells us is that if you take a chunk of gold, which we know to be very malleable, and then reduce its dimensions to 200 or 100 nanometers, it becomes the strongest steel. Wow, well that's a lot of strengthening, right? But now, take exactly the same metals, gold, platinum, copper, nickel, and deposit them using a different technique. All of us here do nanotab of some sort. So if you use CVD or sputtering or anything else, and now you deposit them as a thin film, all of a sudden this effect is reversed. It's a more modest size effect. It's not a log plot, but smaller is now weaker. And what gives rise to that is that the atomic level architecture is different, because now this is nanocrystalline versus single crystalline. So now you have this powerful tuning knob. You can tune the strength based on the material's dimensions and a microstructure. But the size effect is even more powerful than that. So what happens if you pull or try to bend a glass rod? This is not a rhetorical question. What happens if you pull out a glass rod? It'll shatter and break, right? Glass is not supposed to be extendable. So this is a special kind of glass. This is a metallic glass. It's about 150 nanometers in diameter. And we're going to pull at it. So 150 nanometers in diameter, and watch this region right here. So we're extending a glass. And it's extending and extending, and look what it's doing. It's forming a neck. And it's actually extending by more than 100% before failure. Glasses are not supposed to do that, right? And I'd like to show you one last example. So this is a ceramic nanotruss, and this is a single unit cell. And we're going to compress it now. And watch what happens to these outer beams. So they're slightly elliptical, and so they're bending. Imagine bending a piece of chalk. You're not going to be able to. It'll snap. But these ceramic, this is ceramic titanium nitride. This nitride nanolattice, first of all, each beam is deflecting so much so that the temporal stress here is something like 1.7 GPa. Ceramics are not supposed to stay intact when you apply 1.7 GPa of tension onto them. But these are staying intact over multiple cycles. And so what that tells us here is this. Sometimes materials get stronger. Sometimes they become weaker. And some other times you can suppress brittle failure. All of these beneficial phenomena emerge only at the nanoscale. And so the big question we had was, how do we harness this phenomenon? Can we harness this phenomenon and then proliferate into the larger scales to make macro-sized materials? So just a few words on the architected materials. So instead of using UV lithography, which is I think what many people use here to define two-dimensional features, we use something that's called 2D lithography using a less powerful laser. But we flood, it's called a two-photon lithography, so we flood the space with a lot of photons. And so the constructive interference of two photons in a single laser pulse produces a sufficient amount of power to cross-link the polymer in that voxel. So what you see here is this tiny little voxel, so that allows us to eliminate these diffractive cones of the UV light. So less powerful laser, but a lot more photons. And so this two-photon lithography technique allows us to then sculpt whatever complex shape we want. So complexity comes for free. It doesn't have to be periodic. It doesn't have to be any specific shape. I can write a nano version of each one of you in the audience here using this technique. Now, after we write the scaffold using this technique, we actually coat it with the material we are interested in. So maybe not necessarily polymers, but it could be a ceramic, it could be a glass, it could be a semiconductor, or metal. And then, usually we make our samples in these cube form factors. So we expose some of the faces of the cube, and then that allows the oxygen plasma to access the tubes and the material inside. And so we etch out this scaffold that was so painstakingly written. So what we end up with is a replica, the hollow tube replica of what we had designed, and that's what allows the materials to be so rich. Now here's the real-time process. of writing using digital nano-Architected instruments. So you can see that we first define the field and then we start writing, and this is real time. It's a pretty fast process, but not exactly manufacturing. Now, everything we make is very small. I'd love for it to be bigger, and maybe somebody here could help us scale this enough. But because everything is very small, we have to do a lot of our experiments in this special instrument. So without all these whistles and bells, it would just be an SEM chamber, just a scanning electron microscope. But now we have a nano-mechanical module which allows us to use all these different inquisition devices. So we can do tension, compression, we do a lot of different kinds of mechanical perturbation that allows us to study these materials and how they deform at multiple length scales. So here's a big question. This is an architecture, all made out of alumina. So how many of you have done ALD, atomic layer deposition? 1, 2, all right, not a lot. So the ALD community, they're very proud of what they do. And they'll tell you, oh yeah, we can deposit anything as long as it's aluminum. So this is alumina architecture, and the wall thickness here is 15 nanometers. All right? So imagine your coffee mug with a severe case of osteoporosis, and we're going to compress it. We're going to stuff it. So what do you think is going to happen? Very brittle, very thin wall, very porous. It's going to crush it, right? And we're going to destroy it. So here we are, we're compressing it in that instrument that I just showed you. And here's the stress rating, and sure enough, it loads up, and it crushes and dies, and it's catastrophic, and it's bad news for this guy. We have a little nano cemetery in our instrument. And there is actually one good thing. Look at the stress level here. So it exceeds 25 MPa. Something that's 99.9% air shouldn't have anything measured in mega units. It could be kilopascals, it could be pascal. So this is still very strong. So we're not sacrificing strength. Oh, okay, all right. So we crushed, but it's still very strong. So we repeat this experiment on something that should crush and die even more readily. So this is exactly the same architecture, the same process, everything is exactly the same. But now we reduce the wall thickness by a factor of 5. So it went from 50 down to 10 nanometers. And now watch what happens. So we're compressing it, we're ready for it to crush and die even more readily. And you see it's compressing it almost to halfway point, so about 50%. And now as we're approaching the point where, wait, it should be breaking, but instead it's recovering. So my former student Lucas made a ceramic sponge. This particular ceramic thinks it's a sponge. So if that doesn't prove to you that there is in fact a size effect, right, so the materials behave very differently at the nanoscale, I should drive home to Bethany right now. Now, this behavior actually prevails in very complex geometries and under very complex loading states. So look at, this is a bicontinuous, we call it nano-labyrinthine type of a surface. So there are no beams here. This is all a bicontinuous surface. Now, this is a periodic, this is aperiodic, and what you can see is that it's recovering over multiple cycles, and you can see there's quite a bit of energy storage and energy absorption capabilities. You can see that the density doesn't have to be homogeneous. In fact, we can prescribe different density regimes. So watch what happens when we compress this one. So there, of course, this is the lighter, this is the less dense region, and so that's the first region that's being compressed. And then this part doesn't even know that it's being subjected to any kind of mechanical loading. And then only after we've fully densified and compressed the bottom part, this becomes the load-bearing element. And so now you can prescribe different architecture and different trajectories of how and where your material is going to reform. Now, look at this very complex shape. So now each beam is a fractal. And so now we have these, it's made out of these self-similar units within each beam. And you can see the kinking here. So we're expecting the failure to occur right in these kink locations as we're compressing it. And it's recovered. So all of these examples are all very brittle, very brittle materials that should instantaneously crack, so they don't. So, well, of course, we wanted to know why this happens. Well, so it turns out that hollow beams, which is what the key element is in most of these architectures, undergo a process called shell buckling. So that's an elastic instability that is what might be the mechanism for what allows the structures to recover. Well, it turns out that for these kinds of deformation processes, you need to meet a particular criterion. So if you have a beam whose thickness is T and whose radius is A, and you compress it, for it to be able to undergo shell buckling prior to failure, we have to have a certain T over A critical ratio. And so for this particular material, for the alumina, that critical ratio turns out to be something like 0.08. Okay, all right, so we see that maybe that's what explains the recoverability. Well, sure enough, Let's look at that. So for the 10 nanometer wall thickness, that ratio is below the critical ratio. And so we can see that for various unit cells, your structure always recovers, so that seems to be consistent. And as we increase the wall thickness and we get to the critical ratio and then deviate further and further from it, our deformation becomes much more stochastic, much more jerky, and then just, obviously, this guy doesn't know what to try to recover. So the answer lies in mechanics, right? So what that tells us is that if we were to build a building out of big tubes whose wall thickness is 10 centimeters and whose diameter or radius is 3 meters, and we preserve the T over A ratio, and we build a building like this, some giant comes and steps on it, it'll just spring right back after, right? Right? Would this ever happen? Okay, girls smiling, this is good. So most of you are awake, this is good. But this would never happen, right? Why not? How does this size effect manifest itself here? Because it's not explicit, right? It's all about T over A. Mechanics tells us as long as the T over A is preserved, we should be good to go. Why would this never ever happen at the macro scale? And why is it that we're benefiting from the nano-sized effect there? Any ideas from students, possibly? These are other students. I heard something. What? Buckling. Buckling does not happen. That's the problem. Why would that not happen? What would happen before buckling? Yield. This is concrete. This is concrete, like serious building material. What is yielding in a brittle big concrete? You're right, but how does yielding happen in a brittle material? It just fractures. That's exactly right. So there's so many, it's the defects. There are so many defects, micro voids, micro flaws, that when we globally apply any kind of stress, the local stresses on all these defects will be so much higher than the fracture strength. The material will always fracture locally before ever getting a chance to buckle as a structure. So this material doesn't ever get to experience any kind of buckling because of defects. So the probability of finding 83 resilient defects in something that whose wall thickness is 10 centimeters is 100%, many defects, and they're not clumsy. In contrast to something that's only 10 nanometers thick, first of all, the probability of finding a flaw is very low, and secondly, the size of the largest flaw is only 10 nanometers. So that's not a weak flaw in any way. And so what that teaches us is that we are able to, the size effect manifests itself here by our ability to make much more ideal, much more perfect materials when they're only 10 nanometers thick, and you can fill up the whole room with them. And when you make something that's much thicker. All right, so now the question was, did we hit the white space? Remember, that's what we were after. So all of this is to remind you, this is the white space before, and these are all of our points, and so you can see that at least in these hierarchical fractal nanolattices, we bought ourselves 2 more orders of magnitude of reduction in relative density, and you can see that we're certainly, this was so 4 years ago. We can do much better than that, and you guys can probably do much better than that. But we certainly are showing that combination of the nano-size effect in architecture does in fact provide a pathway to build these entirely new classes of materials. And what we're learning is that at least in part of it, we can get to the theoretical limit, especially at the larger density regimes here. So here you can see we're in the lightweight regime here, and we're pretty far from the theory, from where it's possible to go. But in the carbon materials, and I'll spend a little bit of time talking about this, we are in fact approaching the theoretical limit, which is very encouraging. All right, now, what I'd like to tell you is some of our latest work. So let me bring up this plot again. So the theoretical maximum that I'm plotting here has a certain slope, right? And now when you look at some of our data points, you might be scratching your head and saying, well, I only have 5 minutes left, oh my God. Saying this scaling is really far from ideal. And then you're wondering about this, well, it turns out that it's all about the nodes. So these nodes really kill us. So we figured out that maybe what we could do is create some architectures that don't have any nodes. And so what I'm showing you here is some of our very recent work. So this is my new student, Greer, who's creating these woven architectures. You can see they don't have any nodes. And so what we're effectively doing is, look, we're pushing and pulling on a rope. So we effectively create the net. And so you can see we can actually extend them. So far I've only shown you compressive results, but these are actually tensile results. And then now immediately go into compression. And so we can push and pull on them. My colleague Dave Barr used to tell us all the time, don't ever push on a rope. Well, it turns out that when you create nano ropes, you can actually push and pull on ropes, and they work pretty well. Okay, that's just to show you that they're actually quite a bit more extendable than anything that's not woven. So we were encouraged by that as well. Now, this tensile capability allows us to study fracture of these materials and trying to understand how do you think of fracture in something that's fundamentally made of flaws, right? This material is continuing when you zoom out, but it's very discrete when you zoom in because it's all made out of tubes. And so here's what we learned. We learned that they always fail orthogonally to the loading direction, no matter which way the defect is oriented. So that gives you a certain amount of comfort because you can put in a notch or a defect in any orientation that you want, and it always fractures orthogonally to the loading direction. And by doing this, we learned that we can actually hit another white space. So these materials don't ever cease to surprise us. Now, this is doing fracture the right way. That was not the best way to do fracture. So now I have a summer student who figured out that this is how you should really do fracture. So the way you do it is you actually create single edge notched specimens, and so that you can apply the load homogeneously. And so these are the kinds of geometries that they're testing. And sure enough, of course, they've already made it. This is the thing about Caltech. Their students are kind of brilliant. And so they really figured this out. They're able to track the crack opening, the crack trajectory, and the crack propagation here. And so we're able to track the displacement and quantitate structural toughness of these materials. And this is usually when I take the dramatic pause when I have 5 minutes left. Because this is a lot of pictures and videos and mechanics that I showed you, but many of you probably don't care about mechanics. And usually, I think I ask my audience to choose one of these topics because I can't tell you everything. So we work a lot on additive manufacturing, we work a lot on energy storage, we work a lot on mechanics, but I don't have time to tell you any of these stories really. And so I'm just going to share with you some of the highlights of what we learned that's exciting to us in the last little bit. So additive manufacturing. Are people interested in additive manufacturing here? Seems like this would be functional material. So what we've discovered is that you can actually track various ions in the resin. And so, for example, this is some kind of a moth effect. So we trap a nickel ion in this organic shell, and you can then undergo a ligand exchange reaction. And so you can create an acrylic-based resist to start creating these architectures out of metals, so that we're not only limited to polymers. And so what my student Andre was able to show is that you can make a nickel-containing resin and then pyrolyze it, which is a fancy word for burning. And when you burn off all the organics, you end up with an additively manufactured nickel material. And so you can see the unit cell size here is only 2 microns, and each individual beam is less than 500 nanometers. And that's not something that additive manufacturing people have accomplished to this point. So here's some legitimate mechanical data to show you it is in fact nickel. It should be really crappy nickel. It's very nanocrystalline, very nanoporous, not entirely pure, but look how much better it does than everything else today. So this is the specific strength as a function of beam size. And this is what everybody can do. And what that shows is this is actually quite eye-opening. This is all the additive manufacturing processes available today. And it shows you a tremendous rate at which the strength drops as you try to reduce the dimensions. So when you go from 1 millimeter to 100 microns, you lose 2 orders of magnitude in strength because the other additive manufacturing processes all suffer from defects, and so the defects are detrimental. And what we're learning is that this thing, we have to put in a huge break in the scale here because the nickel we made in this work, let's see, so this is 100 microns and we're at 500 nanometers, so 3 orders of magnitude reduction in size, and this is where our strength is. So our strength is comparable to something that's about 100 microns to 100 millimeters in other metals. So it turns out that our materials are actually quite robust against defects, and so nanoscale is good. So now for metals, we're moving on to metal oxides, and my student Daryl figured out that you can do hydrogel-based synthesis, so no more acrylic stuff. This is actually all water-based, all aqueous, and you can use metal salts. So this is a way to make zinc oxide, for example, using this hydrogel-based synthesis. And so legitimately, zinc oxide, and what do we know about zinc oxide? What's the most prominent properties of zinc oxide? Piezoelectric, right? And so here's what we discovered is that when you compress it, this is the zinc oxide part, it undergoes a voltage drop. So it preserves its piezoelectricity, and here's the unexpected part. If you look, those of you who speak TM, if you look at this, it's very, very nanocrystal. Piezoelectricity is exhibited by what kind of zinc oxide? Single crystalline, right? Because we're creating a field by the virtue of the domain separation. So when you create the electric field in a single crystal. But these are all nanocrystals, so they should all cancel out. Well, it turns out we actually understand now why this is happening. But even though this is nanocrystal, crystalline, we're still getting the piezoelectric response. Now you can make very complex architectures that still exhibit piezoelectricity. So just a few words on carbon, but since we don't have any time, I'll just show you that carbon at the nanoscale thinks that it's not really carbon. So imagine carbon, you're graphite, right? And you're compressing it. So here's a little nano, actually this one's a microfill, it's 2 microns in diameter. Does carbon like to be compressed? Not at all, right? So this is not a carbon nanotube. This is a stubby, chunky, fully dense carbon microfill, or glassy carbon, one of those cryo ones. You can see how much he's not enjoying himself right now. So we're compressing it almost, this is 35%. So carbon at these length scales thinks that it's rubber. Okay, and look at the scale here. This is 7 GPa. Very, very small. So that's just to show you that at the nanoscale, even carbon is different. And actually, we were pretty excited that we just, this work just made it on the cover of Nature Nanotech. So it's a collaboration with our collaborators at Tsinghua University with Wajin Gao and Xiaoyan Li. And just to finish things up, one last one, I promise. So my students are really excited about batteries. Okay, so additive manufacturing of batteries and how do we put them together. So they need some electrochemically reconfigurable materials. So this is a tetragonal nanolattice, microlattice actually. And it's an anode. It's a silicon nanoribbon that's wrapped around the semiconductor. And all we're going to do now is lithiate it. Okay, so look at it from the top. And we're just lithiating it. And watch what happens. This is a silicon anode. It's creating this random-shaped buckle pattern. So what's happening is that we're going from tetragonal into these sinusoidal-like patterns. And so when that happens, so it is a legitimate battery, just to show you, so look, that there's the specific capacity, there's the CD cycling diagram, there's the voltage profile. So it's a legitimate battery. And so it's accommodating the 300% lithiation volumetric extension by these buffers. And so you can actually program the domains and program these defects in such a way that you can now prescribe these defects and make this buckling appear in such a way that you can now induce photonic band gaps. And you can now take this, forget the battery, you can now start manipulating these materials as reconfigurable. And you can see that you can activate different degrees of freedom. You can bend, you can rotate, you can do all these things. And so when you learn about defects, see, materials are just like people. It's the defects really that make them interesting. So when you are able to understand the defects, you can program them. So look at one of these tetragonal microlattices, and now my student Xiaosheng is lithiating it, and lithiating it, and lithiating it, and this is the defect pattern that we pre-programmed. And so you can see that, perhaps you can see the resemblance here with my little logo. Anyway, so this is the end of my talk, and so if you walk out of here thinking, she showed us a lot of really crazy architectures, and I don't remember anyway, please remember just 3 things. If you're clever about 3 things, so that is your atomic level microstructure, so you need to understand if it's amorphous or single crystal or whatever your material is, the architecture of your material, okay, and how it responds to this size effect. You can create entirely new classes of materials, and the reason why we would want to do that is so that our children live in the world where there are no hearing aids. You can just write the bone, the cochlear bone, put it directly in the ear. Our iPhone 83 will not need to be recharged for about a year. The balloons will be, of course, helium-free because we can evacuate the air, right? The vacuum is lighter than air. The Christmas ornaments will never break. And this is our latest pursuit. So perhaps you had some of these outside, right, Brownie? So we're now making chocolate nanolattices, which are 100% taste, 99.9% air, and 0.1% calories. So thank you very much.